So in this lecture, let's talk about resonance. So you might have had an introduction to resonance in physics, but it's not the same sense as resonance. But it strikes a note that it's similar in some aspects. So when we talked about bonds, I told you that there are pi bonds, and whenever you have formal charges and pi bonds, they often spread more than the bond line structure can imply. So whenever you see a bond line structure, for example, consider an allyl carbocation. So where you have 3 carbons and you have a positive charge on one end and a pi bond on the other end. So there is a pi bond on carbon 1 and 2 and also 3. So the pi bond is also delocalized between carbons 2 and 3. Why is that the case? Let's take a look at the actual structure. When you look at the actual structure, you notice that this carbon here, because there is a positive charge, which means that there is a empty p orbital. And when you take a look at 1 and 2, because of the double bond also represents that there is a p orbital that's being bonded between these two. Now, because there is a positive charge, there is also a p orbital that's empty here. Because all three are present at the same time, the electron bonding, the pi bond, can also have formed between these two as well. So because there is no stability of that pi bond, what it causes is it causes a specific phenomenon called delocalization. So delocalization here refers to the fact that the empty p orbital, all the empty p orbitals are already unstable, and they'll also try to jump the electrons between themselves because all of them have the same energy. Notice that all of them are carbons. All of them have the same 2pz orbital or the 2px orbital that's generally empty. Because there is one orbital that's empty, so there is always a choice that, this is a 2py orbital. Because it's all the same orbitals and all have the same energy, it causes the electrons to move from one place to the other place without having any change in the energy. This process is called delocalization. So because this delocalization can occur, the pi bond itself can form between either carbon 1 and 2 or carbon 2 and 3. So because this can happen, so if all of the carbons have unhybridized p orbitals, so then all three of them can overlap on side. So all of them can overlap on side to side. Because all three overlapping p orbitals allow the electrons to move throughout the overlapping area, so we say the molecule has resonance. So resonance here refers to the fact that the electron vibrates itself between all the p orbitals and always present at every single part at all the time, which means that if there is for example, let's say if there is a molecule that's coming nearby, there is a chances that the electron can be here or here or here. So it can be at any one of these places. Because it can be at any one of these places, it causes this understanding of delocalized electrons. Because the electrons are delocalized, this overlapping area where the electron has free movement is called resonance. So this molecule itself is said to be resonant, right? And the phenomenon is called resonance. So why does that resonance happen? Is because look at the actual bonding molecular orbital. Notice that the bonding molecular orbital bonds all three p orbitals to form a region on the top and all three of the blue or the negative wave function to form the bottom. Because it occupies whole of the entire structure, this causes it to create the phenomenon of resonance. So resonance here refers to the idea that the electron itself is delocalized, can be present throughout the entire region. So the electrons are present in the entire region at any point of time. So it's not completely localized, where it's not staying at one point, and it's delocalized where it moves from one point to the other point. So this symmetry is what we call resonance. Now the resonance can happen in one way or the other. What happens here is that the positive charge can be here or it can move to the other side as well, meaning that both of them are the same structures and they represent the same phenomenon, but they have a change in the way the molecule behaves. So how can we use bond line structures in general to describe the positive charge on the allyl cation? So notice that the pi electrons can exist on both sides of the middle carbon. So we can draw two different resonance structures. So this is one resonance structure, this is the other resonance structure. So one way of doing this in a bond line structure is to use what we call the resonance arrow, and the brackets inside these structures are described as one single compound. So whenever we draw these brackets, we say that these are the exact same structures but two different resonance structures. So because there are two resonance contributors, so they can create what we call a resonance hybrid, where the positive charge, rather than being at one point, can be spread over the entire orbital to become partially positive, and the electron, the bond also can be spread across the entire orbital, creating the resonance hybrid. So for example, a nectarine is the hybrid of mixing a peach and a plum. So notice that a nectarine does not switch back and forth between being a peach and being a plum. So it's simply a nectarine all of the time. The same thing happens with the resonance structure as well. The positive charge does not go at one point or does not stay at one point. The same way the pi bond also does not stay at one point. It's also throughout the entire structure. This here is an example of a resonance hybrid. So next. So these delocalized electrons are generally more spread out and they are of lower energy. So thus they are generally more stable. So that is why resonance structures always stabilizes the molecule. So resonance always tries to stabilize the molecule. So because the delocalized electrons cause it to have much lower energy. So the lower the energy, the higher the stability. Now the electrons exist in orbitals that span a greater distance, giving the electrons more freedom, minimizing repulsions. So the electrons spend time close to multiple nuclei all at once, maximizing the attractions. So there is less repulsion and more attraction. This causes a peculiar aspect of electrons where electron capture is not easy. This is the reason why molecules with resonance have higher stability. Molecules with resonance have higher stability. Next, let's talk about charge. So we also notice that there is delocalization of charge as well, because the charge itself can be spread over more than one atom. So the resulting partial charges are generally more stable than that of a full +1 charge. Because they are more spread out, there is a chance that, for example, a negative charge can be attracted on either side of the atom. So a negative charge can be attracted on either side of the atom, rather than a molecule that has only positive charge localized on one side, which means that this negative charge can only be attracted on one of these sides. But here both sides can be accessible at the same time. Because it can be spread over a little, so this causes it to have more stability of the charge. So notice that resonance not only creates more stability of the electrons or the molecule, it also creates more stability of the charge. So because it can stay at one single point, it cannot stay at one single point, and it's much more spread over the entire structure. So how do we show the form of resonance that happens in a molecule, or what is the movement that you can show, or the electron movement? So electron movement is shown by curved arrows. So this is a nomenclature that we commonly use in organic chemistry. Whenever we want to show how electrons are moving from one place to the other place, we use curved arrow. So curved arrows have a tail and a head. The tail represents where the electron pair actually was, and head represents where the electron pair actually goes to. So the sooner you master this skill, the easier the course will become. So notice that the arrow starts where the electrons are currently located, and the arrow ends where the electrons will end up after the electron movement. So we will explore much more of these curved arrows in the next chapter, in chapter 3, because we'll talk more about this in third chapter. But as of now, let's try to focus this on the terms of resonance itself, and let's try to learn some rules of curved arrows. So these specific rules apply to describe the electron delocalization or resonance. Rule 1: never show a single bond to be delocalized. So always use delocalization. Always use the arrow for a double or a triple bond. So notice that whenever you use a curved arrow, you cannot delocalize a single bond. So this is very important. Never delocalize a single bond. You cannot break a single bond. So do not break a single bond. So the resonance occurs for electrons existing in overlapping p orbitals, which means they can only be in pi bonds or lone pairs, not on sigma bonds. So the only way you can do that, so double bond or triple bond, or more commonly for lone pairs. Next, rule 2. Never exceed an octet for second row elements. So for second row elements like boron, carbon, nitrogen, oxygen and fluorine, never exceed the valence shell. So notice that the valence shell of an atom in the second row only has 4 orbitals, which means it can hold a maximum of 8 electrons. Notice that an atom in the second row has 1 s shell and 3 p shells, which means that the maximum they can hold is 8 electrons. So do not exceed 8 electrons, which means when you move the arrow, you cannot have more than 8 electrons on the, or more than 4 bonds on a given atom. For example, when you move an arrow like this here, carbon now already has 4 bonds, so which means that adding 2 electrons causes it to have 10 electrons, so that's a really bad arrow. The same thing with oxygen again. If you move electrons here, notice that nitrogen already has 1, 2, 3 and 4 pairs, so which means that you are adding more than the valence shell. Next, the same thing with oxygen again, it has 1 pair, 2 pairs, 3 and 4, so 8 electrons. Do not give it more than the number that it already has. Next, the same thing again here. Here also it already has 1, 2, 3 and 4. Don't give this carbon more than that. So this is a really bad arrow. So these are examples of really bad arrows. So how do you do second row elements then? So second row elements will generally sometimes have less than an octet, so but just never more than an octet. For example, let's say we have a ketone molecule. So for example, let's say I have an oxygen like this. In this, notice that the carbon here has 1, 2, 3 and 4. But oxygen here only has 4 electrons. So what happens now is that you cannot have more than the electrons, but you can have less than that of the valency. So no more than valency, but less than valency possible. Which means that, for example, I can move these electrons up towards the oxygen, causing oxygen now to have more than the electrons. Notice that now when you have more than the electrons, we have to represent it with a formal charge. The reason we use formal charge here is because you are changing the valency of the electrons. Notice the carbon now, so the carbon here originally had 8 electrons. Now we are removing 2 electrons, which means that this carbon gets a positive charge. Oxygen now has a valency of 6, now it has 7 electrons, so which means it gets a negative charge. So this is the idea behind the carbons and oxygens. So whenever you draw this, you can get less than the charge, but you cannot have more than the actual charge. Now, how to draw the formal charges and how to write the formal charges in resonance. So when using curved arrows to derive resonance structures, you will have to often have one or more formal charges to contend with. So to indicate this formal charge, we will have to draw a valid structure. So consider the diagram below, and we'll see how based on the arrows that are moving there, let's try and see if we can draw the resonance structure. So this is the structure, and they have given us 2 arrows where the oxygen's electrons come here and these electrons go here. So these are the 2 arrows that they have given us. Notice that what is happening in this moment here. So here the electron pair becomes a bond. Notice that there are 2 ways of moving the arrow. Either a lone pair becomes a bond, or a bond becomes a lone pair. Especially the bond here generally is the pi bond. So a generally lone pair becomes a pi bond, and a pi bond becomes a lone pair. So here we have a lone pair to a pi bond. So when you move the structures, So when you move the structures, this becomes the double bond, and this lone pair that's here will go here, these two electrons. So this is the structure that we get. Now, so once we have this, notice that there is something awkward about this, where the charges are not the exact same way as it was before, which means that we will have to adjust the charge as well on these structures. So what now we will have to calculate the formal charge. To calculate the formal charge, again check, remember the idea, if it has less than the valency electrons, you get a positive charge. If it has more than the valency, you get a negative charge. Now notice the carbon that is there. So let's say, for example, here you have 1, 2. So let's take this carbon first. So there is 1 electron, 2 electrons, 3 and 4. So there is no charge on this carbon. Next, oxygen. Oxygen has 1, 2, 3, 4 and 5. So oxygen originally has to have 6, but there are 5 there, which means that it has less than the valency. So it gets a positive charge. Next, let's come here on this structure, here at this carbon. So it has 1, 2, and originally there was a double bond. So which means that how many hydrogens were there here? So we have to calculate. So 1, 2 and 3. There were 3 bonds already there. So which means that it has to have 1 hydrogen, and which means that there were actually 3. So there is a hydrogen as well. So 3, but there is 2 for another electrons, which is 4 and 5. So it has more than, so carbon generally has to have 4, but here it has 5, so it becomes negative. So this is the structure that you end up with, right? So let me draw it separately. So you have a negative charge on this, and there are 2 electrons there, so the oxygen gets a positive charge. So this is the formal charge structure when you move the curved arrow. Remember that when you move electrons, always try to check the formal charge. So always try to check the formal charge. So whenever you move a curved arrow, always try to check the formal charge, because once you know the formal charge, you can easily find out what type of movement can happen in a resonance structure. Now, so how to recognize a resonance pattern? So this is important, because when you look at a molecule, you will have to understand how the resonance pattern actually occurs and how to recognize a resonance pattern. So there are generally 5 general bonding patterns in which resonance generally occurs. So these are patterns that you can predict when resonance will occur. So the first one is the allylic lone pair, second is the allylic carbocation, third is the lone pair of electrons adjacent to a carbocation, and 4 is a pi bond between 2 atoms with different electronegativities, and 5 is a conjugated pi bonds in a ring. So the only way you can understand each and every one of them is to do an example, and we'll have to do lots of practice on understanding how each of them work. So let's take a simple one for example. So let's take the first one, which is the allylic bond pair. Now what is an allyl group? For example, let's say I have a structure. So let's say I have an allylic structure here. Notice that there are 2 positions, two carbons that we are looking at. So this is the number 1 carbon, this is number 2, and there are 2 other carbons here and here. The carbons that have the pi bond are called vinylic carbons. So they are called vinylic positions. So this position and this position are called vinylic positions. So carbon adjacent to a pi bond are called allylic positions. So these two that are adjacent to the pi bond are called allylic positions. So if you are right next to a double bond, that is an allylic position, and the double bond itself, the carbons that have the double bond, are called vinylic positions. So once you remember that there is an allylic position and a vinylic position. For example, if you notice that there is a nitrogen here, there is a double bond right there. So nitrogen becomes an allylic carbon, it's an allylic position, and this nitrogen is not adjacent to the carbon, so it is a non-allylic position. Now, what do we need here? We talked about allylic lone pairs. So which means that it's not only allyl, but the allyl position should have a lone pair. So if the allyl position has a lone pair, it means it's a resonance structure. So it can have resonance. So remember that now. So there are two cases that we require: allyl plus a lone pair. So it has to be allyl position with a lone pair, then that causes it to have resonance. So resonance can occur at that position. So let's take an example. Notice that this is an allyl position and there is a lone pair there, so this can have resonance. And here again an allyl position, so our oxygen is at an allyl position. Note that it is adjacent to a double bond, so again it has a lone pair, so it's an allylic position. Again double bond and an atom with a lone pair, again a double bond, an atom with a lone pair, double bond, an atom with a lone pair. All of these positions are allylic positions. Now how do these allylic positions have resonance, or what are the arrows that move? So there are two arrows that show. First, so the first one is that the lone pair forms a pi bond, and the pi bond forms a lone pair. Right, so the first one, the first arrow is lone pair to pi bond, second arrow is pi bond to lone pair. So that is the idea between the movement. Always remember, this is where you start. So this is the start position. Right, so the start is lone pair to a pi bond, and after that you go from pi bond to a lone pair. Next, that ends the final structure. So let's take a look at an example of how this generally occurs. So let's take a simple atom. So notice that this is the double bond and this is the atom directly. So this is an allyl position, and it has a lone pair. So which means that it can have resonance. How will the resonance occur? So again remember, lone pair to pi bond to lone pair. So this is the negative charge. So the first thing that happens is the lone pair to pi bond to a lone pair. So basically the structure becomes, so what will happen here? So these two will get a lone pair with a positive, with a negative charge, and wherever the actual bond was, so the lone pair will get a bond. So this here is the resonant structure. So the number of resonant structures depends on the number of allylic lone pairs. So if you have more than one lone pair, that can also cause more and more resonant structures. So the number of resonant structures depends on the number of lone pairs. So this is number one, where you have an allylic lone pair. So let's review the first pattern again. So remember that when we took allylic lone pairs, there are allylic lone pairs where the lone pair can have charge, cannot have charge as well. So the first example that we saw is where the allylic lone pair had charge. Let's take another example where there was originally no charge. For example, let's say I have so let's say this is the atom. Now notice that this is the vinylic position, so this is an allylic position. So there is an allylic position here. Now, so let's take this example now. When you take this structure, how will the electrons move? So notice the first thing is from lone pair to a pi bond to a lone pair. Now in this structure, so what will happen? So remember that why do we draw double arrow? Because both of them can exist at the same time. So now using this structure, now what will happen to the double bonded structures there? So the two electrons that were there will form a double bond. So they will form a double bond, and the double bond will form two electrons here. Now we want to check the actual charge. Notice that oxygen itself is losing the both pairs of electrons, so which means that it's going to get a positive charge. Why positive? Notice that the electrons is 1, 2, 3, 4 and 5. So oxygen originally should have 6, but oxygen here has 5, so which means it's going to have a positive charge. So less than the valency, positive. Next, the carbon here, let's take the carbon here. Originally it had 1 electron, 2 electrons, and there are 2 hydrogens. Now here there is 2 electrons extra, so which means it's going to get a negative charge. So carbon generally has 4 electrons, but carbon now has 5 of them, so it gets a negative charge. So notice that originally there was no charge on both of them, so now both of them get a charge. So which means that when you take away a lone pair, so the lone pair donor becomes the positive charge. So the lone pair acceptor becomes negative. So whichever donates, for example, oxygen here is donating its lone pair. So basically, it is a lone pair donor, and this carbon here is a lone pair acceptor. So which means there are going to be changes where it causes the lone pair donor will become positive, the lone pair acceptor becomes negative. So if the allylic atom is neutral, then it will become positive, the bottom receiving the lone pair will become negative. So this is the idea behind the resonance patterns in these structures. So always remember that there are generally 2 arrows. So the 2 arrows are, so the first one is from lone pair to pi bond, then from pi bond to lone pair. So this is the common directionality of the structure. Next, let's talk about the second one, allylic carbocations. Remember, carbocations are negatively charged atoms, so positively charged atoms. So carbocation is a positively charged carbon. So let's take a simple example. So again, remember that this is an allylic position, plus it should be a carbocation, meaning that it's a carbon that has a positive charge. Now there is a positive charge here with a carbon. So in these structures there is only one arrow that represents the resonance. So what happens here is the double bond, we draw the arrow from the double bond onto the next adjacent bond, so to the carbon that holds the positive charge. So what happens when this structure completes? We end up with the double bond moving, and the positive charge comes to the bond, so wherever the bond was. So basically it flips the structural integrity basically. So think of it like a mirror image. So this is how the actual structure moves. So and there is only one arrow, you don't even need more arrows, you can just use one arrow. So there are chances that you might see carbons with multiple arrows as well. For example, let's say you can have multiple moments, multiple charge moment. For example, let's say I have a structure like this. So let's say I have a structure like this and there is a positive charge here. Notice that this is still an allylic position. So what happens now? This one, this double bond moves here, this double bond moves here, this double bond moves here. Notice that all of them are not going to happen at the same time, so which means that there's going to be multiple resonance structures that are going to occur. So let me take this separately. So let's say this is the structure. When the first arrow happens, so the structure will happen. So the double bond will come here. The positive charge will take the place of the carbon. Now again, the second time it will happen again, it will move here. This causes it to again move the actual charge. So again, so notice that the double bond was originally here. So now the double bond will come here, and then the positive charge will basically go here. So you don't need to represent that as an arrow. So remember that we do not represent the motion of the positive charge, we represent the motion of the electrons. So arrows, why do we not represent the motion of the positive charge? Is because arrow is the representation of electron movement. Right? It's only showing the electron movement, not the positive charge movement. So the electron here is the pi bond. So again, this one moves here. So that gives you the final structure. So you get the double bond here, here, and then here. So you end up with the final positive charge ending up here. Now note down that all of these are resonance structures of each other. So all of these come under the same wing of resonance structures. So how do you know how many resonance structures it will have? Basis on the number of double bonds and that it has with a positive charge. So if you have one carbocation and three double bonds, you end up with 4 different resonance structures. So this is the understanding of the structures here. Now let's continue with the third one, which is a lone pair of adjacent. So a lone pair that is adjacent to a carbocation. So what we saw before is where you had a allylic lone pair where you had a double bond adjacent to a carbocation. Next one is a lone pair adjacent to a carbocation. So for example, let's say this is the lone pair and this is the carbocation. So when the entire structure works out, so there are 2 arrows that we want to remember here. So the first thing is the lone pair goes down to the double bond and completes the final structure. So again, remember only one arrow when you have a carbocation. So this lone pair comes down here. So what will happen? This basically loses the lone pair and you end up with a double bond. Notice that because there is positive charge, which means that this positive charge lacks an electron. So that's the reason why it's positive. So when you give both the electrons there, it satisfies the structure. Notice that now the carbon has 1, 2, 3 and 4. So 4 bonds, so there is no formal charge. So because the carbon has valence, so carbon has octet. So it has 8 electrons around its shell. So there is no formal charge. So whenever there one will formal charge occur, only when it has less than its valency. Notice that this positive charge occurs because the carbon now has 1, 2 and 3, only 3 electrons. Carbon originally should have been 4, but carbon, because it has 3, it becomes positive, so that's why it's a carbocation. So what will happen in this structure here? So the lone pair balances the charge. So the lone pair balances the charge. So this is the idea behind the structural moment. So remember that how the formal charges are affected by the electron movement in two examples. So depending on how they always try to calculate the formal charge, whatever is the case, always try to calculate the formal charge after the movement has occurred and see if it has less than the valency or more than the valency. Next, fourth pattern is when you have a pi bond between atoms of different electronegativities. So what happens here? Let's take an example. So let's say I have carbon and oxygen double bond. So the third pattern is pi bond between atoms with different electronegativity. So here you have a carbon double bond oxygen. So when you have the electronegativity difference, it causes it to have resonance structure. So what happens now? This double bond goes to the oxygen and results in a charge on the oxygen and a positive charge on the carbocation. This becomes the difference. Why will the oxygen be the one which takes the electrons? So the idea here is the electrons move towards atom with higher electronegativity. So when you compare carbon and oxygen, oxygen has higher electronegativity. So which means that oxygen gets a negative charge, and so oxygen becomes the negatively charged atom and carbon becomes the positively charged atom. So whichever has higher electronegativity will get the electrons, whichever has lower electronegativity will lose the electrons. So here between carbon and oxygen, carbon becomes the cation or oxygen becomes the anion. So carbon gets a formal negative charge and the carbon gets a formal positive charge. So this is the idea behind when you have a pi bond between atoms with different electronegativities. So these two structures represent the extreme descriptions of a pi bonded electrons. So meaning that we are not equally sharing them, but we are equally sharing them versus not shared at all. So the actual compound is a hybrid of both the two. So you will get both mix of both of them. Next, the last one is a conjugated pi bond in ring. So whenever you have each atom in a ring has an unhybridized p orbital, so it can overlap with its neighbors. For example, notice that if you take a benzene atom, so this is an atom of benzene. So when you take an atom of benzene, so this is an example of what we call a conjugated pi ring. Why is that the case? For example, let's say that we move this double bond to form a lone pair. The lone pair then again comes down, so this causes it to move this one here. This double bond moves here. Because this happens continuously, what will happen here is that the bond itself will try to adjust to the structure. So what will happen here, basically there is double bond, so this one coming here will cause it to move down here, this one will come here, this one come here. This is an example of a conjugated pi ring where the electrons are always trying to move over one another. Why does this happen? So it happens because all of them have only one p orbital. So all carbons have one p orbital and all of them form a ring. So because they form a ring, they create a resonant ring. That is the reason why conjugated pi rings are generally the most stable of all compounds. Most stable out of those all compounds, because the electrons are equally distributed throughout the molecule. So that is the reason why sometimes a benzene can be represented as a hexagonal structure with a circle in the center. The reason it is represented this way is because the circle represents the distribution of electrons. So the circle here represents the distribution of electrons, because it's throughout the entire ring, so it shows you that the structure is that way. So this is the summary of all the 5 main patterns. The first one is an allylic lone pair. So where you have 2 curved arrows, where you move from a lone pair to a pi bond to a lone pair. Next one is an allylic carbocation, where you move the pi bond and you replace the, you basically skip the, you're basically exchanging the pi bond with a positive charge. And when you have a lone pair compared to adjacent to a positive carbocation, that also requires one curved arrow, which generally balances the charge. And when you have a pi bond between 2 atoms with different electronegativities, again only one curved arrow, you just need to use that to create the charge difference. And the final one is conjugated pi bonds in a ring. Now conjugated pi bonds always occur when you have the number of pi bonds becomes half of the carbons. So when you have half of the carbons, which here notice that there are 6 carbons there, half of the carbons is 3. If there are 3 pi bonds in a 6 carbon ring, it creates a conjugated pi bond. So if you have a number of pi bonds is half of the carbon, so this is called as a conjugated pi bond. And this generally only occurs with even numbered rings, not with odd numbered rings commonly. So most commonly occurs with even numbered rings. Right? And all of them try to check the formal charge. How do you check the formal charge? If it has less than the valency, a positive charge. If it has more than the valency, a negative charge. So let's try and recognize the patterns again. So let's start with the first pattern. Remember all the patterns. So the first one is an allylic lone pair. Second one is an allylic carbocation. Third is the lone pair adjacent to carbocation. Number 4 is pi bond between 2 elements with different electronegativities. And number 5, a conjugated pi ring. So let's start with the first allylic lone pair. So notice the allylic structure. So what are the allylic? Where are the allylic positions in this structure? So this is an allylic position. There is a lone pair there, allylic lone pair. Again, you have an allylic structure here, but there is no lone pair there. An allylic structure here, but there is no lone pair there. So let's not do that. Now let's do all the allylic parts. So this here is an allylic structure. This is an allylic position. So those are all, they do not have any lone pairs, so remove that one. So the next one is an allylic carbocation. So the allylic carbocation here is an allylic structure next to positive charge. So notice the allylic position here. This is a positive charge on the allyl position. So the third one is lone pair adjacent to the carbocation. So if you have a lone pair adjacent to a carbocation, so notice that there is a lone pair here. So nitrogen has a lone pair allyl next to a carbocation. Next, a pi bond between two elements with different electronegativities. Notice that here there is a nitrogen that's bonded with, there is a double bond between these two. So that's the fourth pattern. And fifth pattern is a conjugated pi ring. So there is no conjugated pi ring here because there is no a ring with multiple pi bonds. Now let's write down the pattern first. So this is the first pattern, allylic lone pair. Next, this is the second pattern, and this is the third pattern. So this is the fourth pattern. So this also qualifies as the fourth part as well. So because between these two here, so between these two, let me write it here, between these two, so this is the second pattern and this is the third pattern. Now let's try and draw the actual structural, how to move the curved arrows, how to push the arrows. So let me So we have the structure now. So let's look at the first pattern. So the first pattern is between these two positions, right? So between here and here. So this is an allylic position, so which means that, remember the structure, lone pair to pi bond to lone pair. Now how will the arrow move here? So there is a lone pair here. So lone pair to a pi bond to a lone pair. So that's the first arrow. Next is the allylic carbocation. So carbocation, what will happen? The lone pair and the positive charge, so it will move towards the positive charge. So allylic carbocation, but there is no allyl position right next to the carbocation. Notice that this is the allyl structure, so which means that this double bond will have to move here. So that's the third arrow. Next, you have a pi bond between the two structures. Notice the next one is a lone pair adjacent to a carbocation. So a lone pair that's adjacent to a carbocation. So what will happen between these two? So this will come here. Right. Next, the fourth arrow is the final one between this carbon here. So this carbon here and nitrogen here. So there is a pi bond there, which means that the lone pair will go to. So remember the pattern here. So one curved arrow from the pi bond to the atom. So from the pi bond, it will go to the nitrogen. So that's it. These are the curved arrows that you get here. So, but what did they ask you here? So they asked you to recognize and use curved arrows to push the electrons and show their delocalization. So that's it. So this is the delocalization that occurs in the structure. So let me write it clearly. So this is the delocalization of the electrons and how they will end up moving. So if you understand this, so then this entire chapter will become easier for you in the coming parts. So in the next in the next lecture, we will talk about how to draw the actual resonance structures after pushing the arrows. So now that you are familiar with these structures and how to move the push the arrows, so try to draw the resonance structures for the compounds that you see here, and try it on your own and try to recognize the pattern. So the two things that I want you to do is, first, recognize pattern, and number two, try to draw the arrows. So try to draw the arrows. So if you are doing these two, then third, draw the resonance structure. So if you are not familiar with drawing the resonance structure, at least try to do 1 and 2 for all of the following problems, and we'll come back to this and we'll try to draw more and more resonance structures in the next lecture.